everyone. Welcome to ClimTip webinar. My name is Quad. I am responsible for communications in ClimTip project, which is an EU-funded project on climate tipping points. And we have so far covered several Earth systems elements, going from the Greenland to the Atlantic Ocean circulation and the Amazon rainforest. And today we are going to the Antarctic. We have Javier Blasco Navarro as our guest speaker. I'm excited to hear more about the tipping points in the Antarctic. Just to quickly introduce Javier, he did his PhD in Madrid at the Complutense University of Madrid, focused on the Antarctic evolution from the last glacial period to the future. And then he did a postdoc in Brussels, at the Free University of Brussels, studying the stability of Antarctic ice shelves and its sensitivity to crevasse formation. And now he joined ClimTip and Alexander Robinson's team at the Alfred Wegener Institute in Potsdam, where he is assessing tipping points of continental ice sheets, including Greenland and Antarctica. So yeah, welcome Javier, and the floor is yours.
Okay, well, thank you very much, Quad, for this introduction. And hello, everybody. I cannot see you yet because I'm presenting mode, but I hope I can see you afterwards. So what I will present here is a work we published regarding the Antarctic tipping points, which were triggered during the Mid-Pliocene warm climate. This study was part of the previous project, the TIPES project, which is very much related to this ClimTip. We were also looking for tipping points. And well, my main focus is tipping points of ice sheets. So I will start just introducing a bit about ice sheets processes. And well, ice sheets are components which are quite simple. Basically, the ice forms because of snow accumulation. The snow accumulates, and as it accumulates, it starts to flow because of gravitational attraction. However, as this snow falls, usually it falls here in this what we know this accumulation zone, we reach into an ablation zone, a region where temperatures are high enough so we can start to have melting at the surface of ice sheets. And well, usually we distinguish between two parts of ice sheets. One, which is the grounded ice. So here it would be the ice that is grounded on a bedrock. And the other part, which is floating ice, which is ice when, if it reaches the ocean and it is not deep enough to touch the bedrock, it starts to flow. So usually the grounded ice is the ice that contributes to sea level rise because it is grounded. It is touching the bedrock. However, floating ice, you can do this experiment. If you have a glass of water with an ice cube and the ice cube melts, the sea level still stands the same because it is already contributing to sea level rise. So the mass balance of a grounded ice sheet is quite simple. It is equal the accumulation, so the ice that falls, minus the surface melt. So if temperatures are high enough, it starts to melt at the surface. Minus the basal melt, in this case, because it is grounded ice, it is the melt induced by the geothermal heat flux, so the heat at the base of the bedrock, and minus the ice discharge, so the ice that passes to be grounded ice to floating ice. By the way, the definition between the grounded ice and the floating ice is what we call the grounding line. And in this case, it would be this point here, where grounded ice becomes floating. And on the other hand, we have floating ice. The mass balance of floating ice, it is equal to the ice that also accumulates, plus the ice discharge from interior ice, so ice that comes from the interior and then flows into the ocean and becomes floating, is feeding the ice shelves. And again, we have a loss of mass due to surface melt, due to basal melt, but in this case, basal melt is produced by the ocean temperatures, and minus calving. Calving are icebergs. So when ice starts to, when ice flows too fast, it cannot stay together at the ice shelf front, and it starts to break. And it's when icebergs form. So knowing this, it's interesting to understand where we are losing and where we are gaining mass in the Antarctic ice sheet. So I will show you quickly this video from NASA. So you know, if we have a white color, it means the mass balance is almost equivalent to 0. So all the mass we gain is equal to the mass we lose. If we have red colors, it means we are losing more mass than gaining mass. And if we have blue colors, it means we are gaining more mass. So here you will see, basically, you can see here the mass loss. We are since the 2002 to 2020, and we see that we have general a decreasing trend. But not only this, you will see that there are 4 main focus of mass loss. One is here, what is called the Antarctic Peninsula. A very high anomaly is here, what we define as the Amundsen Sea embayment. And then we have other 2 regions, here, which is called the Wilkes Basin, and here, which is called the Totem Basin. Now, if we try to understand, all this mass that I'm showing here in this case is grounded ice mass loss. If we try to understand the origin of this mass loss, there are either we have 3 components, either surface melt, basal melt, or ice discharge. Now, in the case of the Antarctic Peninsula, we know that almost this melt is produced mainly due to surface melt. However, I will put the video again. In the case of the Amundsen Sea embayment, the Wilkes Basin, and the Totem Basin, we know that oceanic atmospheric temperatures are not high enough to produce melt there. And we also know that because it is grounded, and the geothermal heat flux is not high enough, the basal melt cannot be responsible for this high anomaly. So the only term which can explain these high anomaly fields is this D, the ice discharge. So I will pass. Sorry, the next slide. Okay, so it's so it's important to understand why the ice discharge is increasing in those places. And for this, it's important to understand the importance of ice shelves. So as I introduced before, ice shelves is ice that is floating, and it does not contribute to sea level rise, but ice shelves play a buttressing effect. So they hold inland velocities. Usually you can see ice shelves is what we see here plotted with these yellow and blue colors. They have many times these concave forms, and because of these concave forms, they hold inland ice velocities. If these ice shelves start to shrink, interior ice starts to accelerate, and so we have more discharge. This is the famous example of Larsen B, which was an ice shelf here. And it is an ice shelf which was quite stable in January 2002, but afterwards it started to break, and in a very few weeks to months, almost all the ice shelf collapsed, and all the interior of the ice started to accelerate. So ice shelves, although they do not directly contribute to sea level rise, they hold inland ice velocities. And we know that ice shelves are shrinking because of oceanic temperatures increase. In particular, we know that here the Amundsen Sea embayment, where we have observed before a high negative anomaly, has experienced one of the regions which is experiencing most oceanic rise. So just for you to have an impression, these yellow regions that have a yellow color represents regions that are highly buttressed. So if that ice shelf disappears, it leads to more ice discharge, whereas regions which have this blue color are ice shelves which are not buttressed or have a low buttressing value. So if we lose those ice shelves, they will not play an important role. Now, what happens if an ice shelf collapses? So here is where the tipping point part comes. As we know, tipping points are positive feedback mechanisms which lead to a nonlinear response of the system. Now, in the case of Antarctica, we have 2 major mechanisms. One is the marine ice sheet instability, and the other I will introduce later is the marine ice cliff instability. So the ice sheet Antarctic ice sheet is grounded over a bedrock below sea level, as you can see here. So it means the bedrock, yeah, it is below thousands of meters. And as you can see here in this region, what we call the West Antarctic Ice Sheet, it can lead up to 2,000 meters of depression. Now, if we know that these positions, which is what we call a retrograde slope, are unstable. So what this means is if the grounding line starts to retreat, ice thickness increases because it is deeper. But because ice thickness increases, grounding line flux accelerates. This is a consequence of the flux condition by Skoof. That Skoof proved in 2007 or 2008, I don't remember. But because grounding line flux accelerates, we have to start to have grounding line retreat. So this leads to a positive feedback mechanism. The other positive feedback mechanism is the marine ice cliff instability. This is a bit more controversial, and it is yet to discuss how realistic it is or not realistic, but this is the idea. If an ice sheet collapses and we have a cliff at the front of a grounding line, if the cliff is high enough, of course it is important that the ice sheet is grounded below sea level. If the ice cliff is high enough, it becomes unstable because of the water pressure and it falls. So if it falls and retreats, if the ice thickness increases, depending on the bedrock, but in this case a plain bedrock is also enough for the ice thickness to increase, then the marine ice cliff becomes still too tall. And because it has become too tall, it falls. So again, we enter into this feedback mechanism. So this has led to identify 3 regions which are prone to instability in Antarctic ice sheet. One is the West Antarctic Ice Sheet. This is probably you know this paper from McKay, which investigated several tipping points of Antarctic ice sheet. I have plotted these same dots, but here in this map, so you can see it. One is the West Antarctic Ice Sheet, which is thought to be prone to collapse for temperatures below 2 degrees of warming. In this case, it's oceanic temperatures. And the other 2 regions are the Wilkes Basin and the Totten Basin. As you see, these are also marine basins, but in this case of the East Antarctic Ice Sheet. And although they are marine-based, they do not reach such high depressions as in the West Antarctic case. So how do we set these warming thresholds for these ice sheets? One way to do is through modeling studies. So maybe you know this paper from Garb et al. What it did is they simulated a present-day Antarctic state. And this Antarctic state, what they did is to perturb with slow temperatures. So they increased slowly temperatures to see how the ice sheet evolved. And what they did observe was basically that if you warm up here this region by around 2 degrees, you start to collapse the West Antarctic ice sheet. And as you increase further, you start to get other tipping points, which in this case is the Wilkes and the Totten Basin. Another way to define these thresholds is through proxy records. For instance, this is a cave in Mallorca, and in this cave in Mallorca, they could infer the sea level stand during different periods. In this case, they estimated, this is during the Mid-Pliocene 1 period, I will come to this later, that sea level had to be around 25 meters higher than present day. And then they can date it, and that's when they say that these sea level records belong to the Mid-Pliocene 1 period. So we know that if if sea level had to be 25 meters higher than present day, then Antarctica had to cross several tipping points. So a way to gain insight into future projections and into tipping points of ice sheets is by looking into the past. So I will introduce now the Mid-Pliocene 1 period. What you can observe here as an evolution, temperature evolution, global temperature evolution of the last 5 million years. We are here in the present. This represents future projections. And if we go back until around 3 million years ago, we reach here the Mid-Pliocene period. Now, this Mid-Pliocene 1 period is an interesting period because we know that CO2 levels were comparable to present day. We also know from temperature reconstructions that projected future temperature emissions will be similar as 3 million years ago. But we know that sea level rise back then was way higher, between 6 to 25 meters of sea level equivalent. Now, this plays a huge role to know if it was 6 meters higher or if it was 25 meters higher sea level rise. So here it's again how it looks like. This is a figure adapted. This is the sea level stand nowadays. This is how much it's contributed during the Pliocene. And this is the sea level, the CO2 record. So we see that we are evolving towards CO2 levels similar to the Mid-Pliocene 1 period, but we still are below in temperatures. So the problem with proxy records is some proxy records estimate low sea level high stands, around 10 meters, which can be achieved just by collapsing, in the case of the Antarctic Ice Sheet, the West Antarctic Ice Sheet. Some sea level records estimate a more intermediate sea level contribution, around 15 to 20 meters of sea level rise. This can be explained just by a collapse of some parts of marine basins, in this case, for instance, the weakest basins. And some locations estimate very high sea level stands. And this can only be explained if we have a massive response from the East Antarctic Ice Sheet. So then the question is, what is how can we gain insight and what is the most accurate prediction in the past? Because we see that our sea level records are very sparse. So what we do is we investigate two sources of uncertainty. We want to study the climatology's uncertainty, but we want to study also uncertainties of the ice sheet, so what we call ice sheet unknowns, in this case, ice dynamics. So for this, what we do is we use an ice sheet model. We use the Yelmo ice sheet model, and it's quite simple. Yelmo solves the dynamics of the ice sheet. And so you need to give it some output, mainly accumulation, surface temperature, oceanic temperatures, and, well, some parameterizations, how we convert ocean temperatures into basalt melt, how ice is calved at the ice front, how the Earth, the lithosphere responds to changes in load, and geothermal heat flow. And with these variables, then we can simulate the evolution of the ice sheet. So in the sense of climatological uncertainties, what we have done is to investigate the PLIOMIP2 ensemble. So PLIOMIP2 ensemble is, in our case, it is 12 GCM outputs. So outputs from general circulation models, and they have simulated, based on CO2 levels and some bedrock conditions, they have simulated the climatologies during the Mid-Pliocene. What we have done is we have taken those climatologies and we have rescaled them into the Antarctic domain. And so what we do is we compute an anomaly. In this case, this is an example of precipitation anomaly. This is an example of surface temperature anomaly. And this is an example of oceanic temperature anomaly. And what we do is we apply this anomaly to present-day fields that we know from reconstruction. Well, not reconstructions. From observations, and we just add that anomaly to obtain climatological conditions from the Mid-Pliocene 1 period. And the other source of uncertainty that we investigate is ice dynamics. So one importance we can estimate from the Antarctic ice sheet the surface velocity from satellite data. The problem is we don't know how basal velocities behave. And the reason we don't know this is because the radar cannot penetrate to the basal levels and measure the velocities. So we need to use some parameterizations to estimate how basal friction behaves. I don't want to enter, this is a bit too technical, but basically we investigated 3 parameters which investigate ice dynamics, mainly the basal friction coefficient at the base, the friction law exponent, which is a Q here, and then an enhancement factor. The enhancement factor tells us how fast ice can flow depending on the position of the crystals, of the ice crystals. And so the thing is, we can simulate for all these parameters realistic present-day states. However, although we simulate realistic present-day states, these present-day states, they don't react equally because we have different velocities. So, sorry. So here you can see just a map of our simulated present-day state and the ice error with respect to the observations. This is the mean of our ensemble. And well, here you can observe the ice. What we have chosen as a realistic present-day state are simulations that simulate a deviation less of 2% of ice extension and ice volume difference with observations. So now that we have this ensemble, this dynamical ensemble, we force these simulations with climatologies from the Mid-Pliocene warm period. And this is what we get. So what you can see here on the x-axis are the different models, climatological models. And what you can see in the y-axis here is the sea level contribution, and here the grounded ice area. So basically the spread between models is telling us the uncertainty due to climatic conditions, whereas the spread in every model here is telling us the uncertainty in ice dynamics, so in dynamical parameters. And as we observe is, except for one model, which is the MIROC-4M model, which contributes a sea level contribution lower than present day, so that means that the ice sheet has grown, all models simulate a higher sea level contribution. However, this sea level contribution can range from 2 meters in the case of the HGM model up to almost 10 meters, 9.7 meters in the case of Easy Earth 3.3 model. So this is telling us that the climatic uncertainty is around 7 meters of difference. On the other hand, the dynamic uncertainty we see it depends a lot on every model. Some models have a very low dynamic uncertainty, like these ones. However, for instance, I think the CSM model is the clearest one, has a very high dynamic uncertainty, up to 5 meters. So the idea is to understand why do we have such an uncertainty in between models and between dynamical parameters. So this is the mean simulated state or Antarctic state for every model. And as you can see, almost except MIROC, they all simulate a collapsed West Antarctic ice sheet, but only a few simulate a collapsed Wilkes Basin. In this case, CSM, Easy Earth, and NOR-ESM. Furthermore, with our ensemble, we can estimate which is the probability of being grounded or collapsed in every case, which is what we are plotting here. So red colors represent cases where 100% of the simulations have collapsed. And as we turn into bluer colors, we simulate cases where the probability of collapse lowers. So we see, for instance, that with the climatologies of Easy Earth and NOR-ESM, our Wilkes Basin always collapses. However, with the climatologies of CESM, our grounded probability in the Wilkes Basin is around 50%. And in the Totem Basin, the CSM model is the only one which predicts some retreat, but not a full retreat. It is around 30% of the simulations that collapse. So the idea is to understand what is the main force that drives such a collapse. And for this, what we plot is, we plot here, what we are showing here are 3 basins, mainly the Amundsen Basin, which is plotted here in red, the Wilkes Basin, which is plotted here in orange, and the Totem Basin, which is plotted here in green. Here we are plotting again the grounded basin, so how much percent is grounded, and with all the spread of our simulations. Here we are plotting the precipitation anomaly, and here on the x-axis we are plotting the thermal forcing, so the oceanic warming. What we observe in the Amundsen Basin is that, except for the one simulation, which is MIROC-4M, all simulations have a collapsed Amundsen Basin. So what is different with this compared to with this model compared to the rest of the models? Well, we observe that the precipitation anomaly is 100% almost. This means that precipitation is similar to present-day fields, whereas in the rest of the cases, except in here, this one, the precipitation is lower than in the present-day case. So we draw the conclusion that these cases, although they have a lower oceanic anomaly, because they have also a lower precipitation, Amundsen Basin tends to collapse. However, in the case of MIROC-4M, we see that although the thermal oceanic anomaly is 0.5 degrees, because we have a precipitation field almost 100% equal as present day, it is not sufficient to collapse the Amundsen Basin. We observe something similar also in the Wilkes Basin. We observe that if we exceed 3 degrees of warming in the ocean, it is the only case when Wilkes Basin collapses. The other simulations which have a lower melting, a lower increase, they do not show any signs of retreat. However, interestingly, although this simulation, the CSM, has a higher warming than the other two cases, because it has also a much higher precipitation, such high precipitation can sometimes overcome the warming. So here in some cases, such high precipitation can lead that it is not collapses the Wilkes Basin, whereas in some cases it collapses. Whereas here, where we have a lower precipitation, we see that for a 3-degree warming, we always collapse. And finally, we show the Totem Basin. In this Totem Basin, we see that even under 4 degrees of oceanic warming, we still do not collapse Totem Basin. However, in the case of the simulation of CSM, which has a very high oceanic warming, 8 degrees, we start to observe a retreat, although this retreat is not as pronounced in the other cases. It retreats only until 85%. So then the question is, which sea level proxies should be considered as realistic then? Because we have still a wide range. And although this is not work that we have done, I think it is something interesting to show, is the effect of glacial isostatic adjustment. So as I showed before, these cliffs from Mallorca, what they do is they measure, this is an example from Mallorca, but they have been doing this in other caves. Basically what they do is they look at the sign where sea level was standing, they do a record of the, they trace it back, and they say, okay, this signal belongs 3 million years ago when sea level was about 25 meters high. The problem of these measurements is that they don't take glacial isostatic adjustment into account. And the idea is this: the Earth, solid Earth, is not static, but it changes depending on the load of ice. So this is an example where we have no ice, so then the Earth would be plain. But as we start to build an ice sheet, here it depresses and here it increases. And as the ice sheet starts to shrink, this part starts to fall, and we reach again this equilibrium state. So recent work using GIA models have been done on the Australian coast. And what they have shown is that if you take into account glacial isostatic adjustment into account, then sea level records from the Mid-Pliocene 1 period lower to 16 meters. So we are not anymore at the high sea level stands of 25 meters. We are now going down to 16 meters. If we simulate also the Greenland ice sheet, I have not shown our results on Greenland ice sheet because they almost all show a collapsed ice sheet. But if we take this into account, our simulations, and we add both contributions, Greenland and Antarctic, this is what we obtain. And I want to show these 3 cases, CSM, EC Earth, and NOR-ESM. These 3 cases are the ones that reach high stands of 16 meters. And all these cases with 16 meters simulate a collapsed Wilkes Basin. So in order to achieve such a collapsed Wilkes Basin, it is enough to warm the ocean by 3 degrees. But we don't need necessarily to invoke this marine ice cliff instability mechanism in order to reach 16 meters of sea level rise. So in order to conclude, these are our results that we obtained with the Yelmo ice sheet model, forcing it with mid-Pliocene climatic conditions. And what we observed is that the West Antarctic Ice Sheet, the Amundsen Basin, collapses with a very small warming, 0.5 degrees compared to present day, but that high accumulation rates can mitigate such a retreat. On the other hand, Wilkes Basin collapses with 3 degrees of oceanic warming. Below, we were not able to collapse it. But again, precipitation was able to reduce such a retreat. And we saw slight retreat in the Totem Basin. However, we needed very high oceanic warming, around 4 degrees. So with this, I will conclude. Thank you for your attention. And of course, if you're interested, this is the paper that we published. It's in Climate of the Past. But if you have any question, you can also make me. So thank you.
Thank you so much, Javier. Yeah, thank you for the great
Should I
and very
should I
concise
stop
presentation. So,
sharing?
I think you could keep your slides because maybe we
Okay.
have clarification questions and you might need to use
Okay.
some of them. Yeah. And yeah, we would open now our discussion and Q&A. If you have any comments, clarification questions, you're welcome to either unmute yourself or write your question in the chat. Okay, we have Jorge over there. Yes, please go ahead.
Hi, Jan has a question.
Yeah. Hello, hi.
Yeah.
Thanks for the talk. It was very instructive. I have a question with respect to the precipitation that you were showing. It's kind of interesting that although the climate gets warmer, the models tend to predict less precipitation. Is it kind of linked also because you actually melt some of the West Antarctic ice sheet and you have less orography to precipitate? Or, I mean, why is that? That although you could have you know a higher precipitation because of the higher temperatures, why you see a reduction there?
Well, I think if you look precipitation by basin, generally the mod at well, for instance, the weakest basin, we see more precipitation overall between models.
Yeah.
It is true that in a Amundsen basin, we see either an equal precipitation or less precipitation. Right now, I don't have because okay, you could have orographic effects, but in theory, we should compensate with these orographic effects. In our case, with a lapse rate factor, which we introduced. I don't have a clear explanation for this, to be honest. I don't know why.
Yeah, no, thank you. I think it's probably somewhat difficult to answer because it's more on the circulation model sides rather
Yeah.
than yours. But it would be interesting to know what is the orography they assume. You know?
I mean,
Because
the orography they assume, I know. They assume orography from the Mid-Pliocene 1 period, which is around 25 meters of sea level higher.
yeah,
Okay? So it is a very small ice sheet. But I would expect that in a small ice sheet, you should have more precipitation. So, not sure.
well, anyways, thank you very much.
Do we have more questions? If not, I can ask a question. I mean, this was a very dense information. I'm not a specialist in a way. I was trying to understand how does that relate to today, because you were comparing the CO2 levels, and they were similar, right? But the temperature is much greater in that Pliocene era. And I was wondering also, like you said that at the 3 degrees of oceanic warming, the Wilkes Basin is basically collapsed. How does that compare to the global mean temperatures? Because I'm not sure if it's the same. It's not, right?
No, it is not the same. Well, first of all, it's a bit tricky sometimes to compare only with CO2 because we also know that during the Mid-Pliocene 1 period, also insolation was different. So I guess if you have similar CO2 levels but more insolation, then you would get more warming. And nonetheless, I think it's a good benchmark in the sense we know that 3 million years ago, the continents were more or less similar, the position to nowadays. And we know that at least from temperature proxies, it was 2.5 to 4 degrees warmer on average over in the world. So that can serve more or less as a benchmark for us to know for the future. However, I don't know how much warming you would need globally to warm Wilkes Basin by 3 degrees. That I cannot explain. But what I think people expect is that in the future, more warm waters are penetrating from the Southern Ocean into the continental shelf, and these warm waters, if they penetrate Wilkes Basin and warm that region about 3 degrees, it could collapse. But I cannot tell you exactly how much it means in terms of global warming.
Okay, yeah, thank you. Just to clarify, and what do you mean by insulation? Insulation was different. Is that something in the composition of the atmosphere?
No, insolation would be the distance between the Earth to the Sun. So we know that the trajectory, it has some cycles. This is called Milankovitch cycles, and depending on these cycles, more sunlight hit the Earth or less. So, and that's what we observe when we see these glacial cycles. And the thing is, I don't know right now which insolation we had during the Mid-Pliocene war period, but if we had similar CO2 levels, but a higher insolation, so more sunlight's coming, that could also explain why we would have a warmer Earth, even with the same CO2 levels as nowadays. Is that clear?
Thank you.
Okay.
Thanks. We have more questions. Sebastian, is that a hand? Yeah.
Yeah, the Zoom design is new. Maybe people don't find their hands anymore. There's something I've never really understood, very fundamental, about the marine ice sheet and ice cliff instabilities. So you showed that in the beginning.
Yep.
Why? So for the ice cliff instability, it doesn't seem to matter what the slope is of the ground.
Yes. Okay. So this has been hypothesized. It can be observed as a calving law for grounded ice. So the idea is the following: if an ice cliff here is high enough because of the pressure of the water that is pushing here, but the ice motion is going in this direction, it would start to fall apart. So the thing is, if it falls and the ice thickness increase, it is important to increase. So in this case, either a plane slope or a retrograde slope would lead to an ice thickness increase. Then because it is still a marine cliff and it has become higher, it would still be higher, and it would lead to a positive feedback mechanism. So you don't need necessarily retrograde slope, but you can have a plane slope. And in this case, because as you enter, the ice thickness is thicker here, we will always have higher cliffs, which will be unstable. However, yeah.
Why does it break more easily when it's higher?
Why it breaks more easily?
Yeah.
Yeah, as far as I understood, it's because here, all this part which is in the ocean is being pushed towards the interior, whereas this part, if it's higher, it breaks because of gravitational pull here, which goes to the right, because ice motion goes in this direction, and the ocean is pulling here, pushing in this direction. I hope it becomes clear.
Yeah, I still admittedly don't understand why it then breaks easier when it's higher.
Well, I mean, if an ice cliff is too tall, there is also more gravitational attraction, no? It is more likely to fall, higher cliffs, no? I mean, if we have just a cliff that is advancing, but we have a force at the base pulling down, whereas the upper part is going to the ocean, I think at some point also gravitational attraction will lead this ice cliff to fall. Nonetheless, it is important to say this is a mechanism which was proposed by the quantum polar, and many people don't fully agree with this mechanism. in partly because it has not been observed in nature, in partly because it does not take into account effects, for instance, of sea ice or ice shelf, which could also play a counter, a melange effect, what is so called. But it has been used in literature to argue that Antarctica could contribute to around 1 meter of sea level rise by the end of this century. So usually the higher end scenarios do take into higher projection scenarios of Antarctica do take into account this marine ice cliff instability. And the motivation was because it could simulate very high sea level stands during the Mid-Pliocene warm period. We do not include this mechanism in our model, and that's why we do not get such high sea level stands. It's just a mechanism which was proposed, and well, what we try to say is we can reach such highly sea level stands without the necessity of including marine ice cliff instability.
Yeah, thanks. That was very clear. Yeah.
Okay, thank you.
Thanks very much.
Paul Ritchie, please go ahead.
Yeah, thanks for the talk. I was wondering if you could probably say a bit more about timescales. So you've presented two different mechanisms. So is one mechanism like faster than the other, and also like in the climate models themselves, how well constrained are like the tipping timescales there? So yeah, thanks.
Yes, I could have included actually the evolution. I have not painted it, but it takes around, in the warmest cases, it takes around 500 years to collapse the West Antarctic. But in order to reach an equilibrium of simulations, we had to run around 30,000 of model years. So I would say West Antarctica usually collapses within 1,000, 2,000 years, but the other basins, it needs larger times, probably larger than 10,000 years, at least in our case.
Okay, thank you.
But you can observe the curves in the supplementary material of our paper. That you cannot find them. You should be able to find the timescales.
I was wondering, I mean, this research is about the paleoclimate, right? And how are you planning to make use of it, or how does it inform the research into the current assessment of tipping point? Because, I mean, I'm just coming from this media perspective where it's very kind of, there's many headlines that says that it's already past tipping point.
Well, I think if we look at this evolution, of course, it's not following a linear, but rather, it merges different timescales. Here it is what we can observe at the glacial cycles of the last 800,000 years. And what we see is there were periods where temperature was higher than present day temperatures, but on a geological time scale, this was on a very short time. So we went high, but then we went down. And I think the projections nowadays, it is not going further, but tend to simulate a warmer scenario, which will be longer for more years than these cases, these peaks. And if we look into this data into the past, we see that the Mid-Pliocene warm period is interesting because it's a moment where these warm conditions were held for sufficient time. So it was long enough during this with these warm temperatures. So I think the reason to look into the Mid-Pliocene warm period, it is the closest time which potentially could resemble the future world we are going to. So it's more just, and because we have some proxy records that we can compare, it is valuable information because it tells us, okay, if we know that sea level was around 60 meters higher, that means that maybe and we know that maybe we need also other models to see which thresholds they have in their ice sheet model to collapse Wilkes Basin. But maybe we know that ocean maybe was 3 degrees warmer, then we can compare to the past and we can predict how it will behave in the future. But I would say that The interesting about this period is just how much it potentially resembles future emissions compared to all these in-between periods.
Thank you. Yes. Yeah, super interesting. Do we have more questions? Something's happening in the chat. Or is this about... Is your question, Sebastian, to Javier?
No, it's not. It's still the same question. Thanks.
Ah, okay.
Becoming more and more clear.
So this is the so-called marine ice cliff instability, which was not part of the model, right?
It was not part of the model.
Right, okay.
Yeah, I should have maybe introduced it more to clarify that it's a bit a controversial mechanism, which is under debate, but some models decide to include it, some not, and it is, and originally the main reason to include marine ice cliff instability is because it could explain very accurately high sea level stands during the Mid-Pliocene warm period. This was the main motivation. But I think there is a bit shifting paradigm because now we don't expect such high sea level stands. And actually, there have been recent papers saying that marine ice cliff instability was included in some models in a wrong way as a retreat rate rather than as a calving law. But this is, I think, very technical and ice sheet related. But well, we can discuss it maybe another day if you are interested.
And since you are also looking at Greenland, I just wanted to have some sort of maybe high-level comparison in terms of the processes of melting in Greenland and disintegration in the Antarctic ice sheets. What are the, like in comparison, what are the dangers or risks comparing the processes there?
Okay, I think I have maybe a slide here. Okay, yeah, here. I think the positive feedback mechanism that affects Greenland is different than the one that affects Antarctica. So in Antarctica, we know that surface temperatures, they are not getting very high, and we are not worried about surface melt. What we are more worried about is oceanic melt, because oceanic melt, what it does is it shrinks ice shelves. Because ice shelves shrink, we lose bad pressing effect, and because we lose bad pressing effect, ice starts to accelerate, and we can get into the marine ice sheet instability, where marine regions, marine grounded basins are prone to this to collapse if we have ice is going to have a retrograde bed slope. However, in Greenland, I think we are not dealing that much with marine basins. We are dealing more with grounded basins. And in this case, what we fear more is the so-called ice elevation feedback. So usually we have an equilibrium line. Above the equilibrium line, accumulations processes dominate, but below the equilibrium line, ablation processes dominate. And if we start to melt, in a warming scenario, this equilibrium line increases. And as it increases, we leave the accumulation zone. And if the ice sheet enters into the ablation zone, we start to, this is the positive feedback mechanism of the Greenland, it starts to decrease. So I don't remember exactly when we did these experiments, but I know that with relatively, well, 3 to 4 degrees of warming, we could already start to observe this mechanism in Greenland. So that's the reason why we always had almost a collapsed Greenland ice sheet. But I would say that in the case of Greenland, we are more worried about atmospheric temperature increase, whereas in Antarctica, we are more worried about oceanic temperature increase.
Yeah, thank you, Javi. Okay, we have another question from Jan or Jorge.
Javi,
Yeah.
so I was a co-author of that paper, so I think I should know, but I don't remember what we did exactly with sea level as a forcing. I mean, so that leads me to the question of how much would you expect Antarctica to retreat its grounding line just from a sea level that is rising. So imagine Greenland was completely gone, plus 7 meters at sea level in forcing.
Yeah.
Would that give something that is negligible or not?
So we applied a constant sea level of 20 meters. And actually, based on our results, we could have even put 10 or 15, because back then we did not have, well, the ice that melts does not directly contribute to sea level in our it does, but not in our model. So we impose a 20 meters higher sea level. Of course, if we have a lower sea level, this would make that potentially Wilkes Basin could be more advanced, because we would have less water pressure, right, if we are lower. But I think I did some experiments and the sensitivity was not very high in it was very similar. But it was because I played at the beginning with some uncertainty parameters, and I found that sea level was not playing a big role. So I almost didn't touch it.
Thank you.
Thank you. I wonder if we have any more questions. Otherwise, perhaps, Javi, if you would like to add anything that you maybe have forgotten to mention?
No. I think
yeah.
I think it was a dense talk also, as you said.
Okay.
So
yeah,
maybe less information is better.
thank you so much. Yes. Then I would say we can
Stop sharing.
yes, stop sharing the screen, and thank you everyone for joining today. I definitely improved my knowledge a lot. I was looking forward with the West Antarctic Ice Sheet tipping points research, and yeah, I just wanted to announce that next webinar on 3rd of December is going to be Mañana Milkoreit. I think I pronounced her name correctly, and she's going to be talking about the governance of tipping points, so implications of Earth system tipping dynamics for policy and governance. So that's going to be our December session. And thanks again, Javier, for your super interesting presentation. And thank you everyone for joining.